to talk about, as time goes by, what's going to happen. We could talk about the value of your house as time goes by. We could talk about the speed of your car. We could talk about the national debt. We could talk about the number of moles you have on your body. What do you want to talk about?
Well, would that really change?
Yeah, actually, old people seem to have a lot of moles.
Yeah, it's true.
I have more moles now than I did 10 years ago.
Don't say
Sad
that.
but true. Here, you want to see them?
No, keep me out.
Okay.
Does it matter what it is?
Okay,
Does
so
all that really matter the actual rate of change?
all that matters is the rate of change. Well, we're going to graph the picture and talk about the rate of change. Okay, so let's say that you drive to London from the booming metropolis of Nacogdoches, right? Okay, so here's what's happening. Let's say here we have time,
From 45.
and here we have distance traveled, okay? So, if you go from Nacogdoches to the city limit, and let's pretend like the first halfway there, you're driving a constant
35.
25 miles an hour.
Well, then you
35
drive far
miles.
too slow to be
Okay.
in town.
I'm sorry, 35 miles an hour.
You ride a bike.
What
it's
would,
okay.
what would that look like in terms of the distance?
Put some numbers on it.
Okay, so here's, say,
An hour.
5 minutes, 10 minutes. Let's say for the first 10 minutes you're going 35 miles an hour. What's going to happen?
At 10, you'll have gone 70 miles.
These are minutes. So after 10,
You would have gone whatever 1/6 of whatever your speed limit is.
1/6 of 35 miles an hour. So I guess you would have gone, let's say roughly 5 minutes.
Yeah.
Okay. So what's going to happen is you're going to be going at a constant rate of speed. Now, if you had a constant rate of speed the whole time, what would your graph look like?
A straight
Flat line.
line.
It would look like a line, and the rate would be the slope, right? So rate equals slope. Okay, so for the first 10 minutes, whoop, that's up to 5 miles.
And then
Then
our
you
speed
hit-
limit goes up to...
Well, then you hit a stoplight, let's just say. For the next, I don't know, 2 minutes, you hit a
You're not doing
stoplight.
anything.
That's going to look like
A straight line at the 5.
Still
a
linear.
horizontal
Yeah.
line, right? And what's the rate of change?
0.
The rate of change, or the slope, is 0, right? Let's say, now this is a little bit of line because this says that essentially you approach the stoplight
And then immediately
and then you stopped. So this is really like you slammed into the back of the semi in front of you and you stopped. Okay, but let's say for some reason that made you wiser and your car is still running. So you come out of that stoplight, and what do? Well, you begin increasing, and you go faster and faster. And of course, you don't want to be caught by the police. You can hear their sirens, so your slope keeps going up and up,
Why
right?
are we running from the cops to Lufkin now? This is got out of hand.
Okay, we're being realistic, but not that realistic. We're running from the cops because it makes good stories for the grandchildren.
And a good graph,
And
apparently.
a good graph, right? So, at every point here, you can talk about the slope or the rate of change. Now, on this part where I'm gradually increasing, you may remember that last time we talked about saying, okay, at this point, what is the slope exactly? Well, you can get close to the slope by saying, okay, at this point x, let's go a little bit bigger. Often we call that x plus h. Let's have like h time go by. We'll measure that, and then we'll measure the slope of that line. That's called the secant line. Or secant line, if you're really looking for vitamin C, right? Okay, so what happens though is as that h gets smaller and smaller, And those secant lines eventually go to a line that just touches the graph at this point. That's called a tangent line. Can you see that color?
That's a very good color.
It's a very good color. That's the one we should have put line instead of line, right? Okay, so that's what we're looking at. That is the derivative, the function that tells you for each point on your graph what the slope of the line is. So you tell it an x value, it tells you the slope of the line. That is the derivative function. Okay. Now I believe that last time we did a problem that was something like this. We said, what's the slope at x equals 1? And we said, well, we need to know how much you've moved. So 1 plus a little bit minus how far you were at 1. So this asks how much vertically have we moved up? Rise over, well, how much have we moved over h? As those points get closer and closer together. Now remember, this is as h gets close to 0, not at 0. So this still makes sense. If it were at 0, it would be undefined. But this makes perfect sense. This is as we get infinitely close to 0. And that makes sense over here, right? If you had points, the closer those points were together, the better you would be able to approximate your speed. Unless they were the same point, in which case you would have no estimate at all. Okay? So really close is good, exactly the same makes no sense. Sort of an interesting thing. The closer the better, but don't be the same. Okay, so, well, that's the value at 1. How would you sort of generalize that? You would generalize that to say, well, I just stuck the 1 in here. There's no real special reason why I couldn't say, well, what's the slope at any point? X. You take the height a little ways after x, the height at x, take that difference, divided by h. That's going to give you a number. That is the slope, sorry, I should say, if that limit exists, it will give you a number. And that number we call the derivative. We denote it with a apostrophe. Okay? And we should write at the end, if the limit exists.
How do you read that? Because to me it looks like
Yeah.
f prime
Agreed.
x.
That's what we'd say, f prime of x.
Okay, okay.
Yes. And actually, if you want to do this function